to start with. So the first one is it's really my pleasure to be here, and because I think ISCB is really fantastic. Can you hear me without microphone?
Well, not very well actually.
Not very well. Okay, I will try to speak louder. So second point was my talk is a little bit out of the mainstream. First, it is about mass spectrometry, the one talk about mass spec here. And second, it is quite computational. Nice, you're good. So third one, I'm still struggling with the jet lag. That means if I'm switching to Russian or to German, let me know. So this work was done together with my PhD student, Jan Henrik Koberg, and it will be about efficient spatial segmentation of large image and mass spectrometric data sets. So, because I know that people are not, they don't know image and mass spectrometry here. So I will first start with the introduction in image and mass spec, and then we'll go to the method and to the results. So, first of all, what is mass spectrometry in general? Mass spectrometry is bioanalytical or analytical chemistry technology, which, given a sample, produces you a mass spectrum, and mass spectrum it is in fact a plot of relative abundance versus mass to charge ratio, and it represents a chemical compounds in your sample. So these are here some examples of mass spectra, and if you see here a high peak, a high relative abundance for this mass over charge ratio, that means might be you have a lot of proteins with this mass over charge ratio or just molecular mass in your sample. And what is imaging mass spectrometry is? So imaging mass spectrometry is interested in spatial analysis. That means we have a spatial sample, like we have, for example, a slice of tissue, or we have bacteria colonies, or we have plant tissue. So what we do, we first take a thin slice of this sample, and we put it on a slide, and then we do some sample prep, and then what we do, so we go over this sample, and we take from each pixel, we take a mass spectrum. That means from one pixel here, so we get one mass spectrum from another mass spectrum, and so on. So, and then we can do a lot of stuff to predict some molecular models in biology, medicine, and so on. So, and if you do not know about imaging mass spec yet, I'm encouraging you to have a look at this review paper we have just recently got accepted in Journal of Mass Spectrometry. So in principle, imaging mass spectrometry is great technology. So there are several types of imaging mass spec now, and so most popular are SIMS and MALDI, and invented in these years. And now every year we have several new technologies, imaging mass spec technologies. So it's mostly used for tissue imaging, but also for plants, tissue imaging, chemical surfaces, and even single cells. So what is an imaging mass spectrometry data set from the computational perspective? So in fact, it is a large hyperspectral image. That means for one pixel we have a spectrum, quite long spectrum. But if we fix MZ value, that means if we fix some value here and we can consider the intensities correspond to this MZ value, so then we'll get a grayscale image. So, and normally the size of this data set is we have around 10,000 MZ values, we have this size of pixels. One data set is around 1 gigabyte. So what's the problem of spatial segmentation in IMS is? So we would like to split our data set spatially. We would like to split it into spatial regions by clustering our mass spectra. That means we would like to split it based only on mass spectral similarity. And once we have this clustering, what we do, so we create a segmentation map, which is just a visualization of our cluster results, where the pixels from the same cluster, we color them with the same pseudo-color. So like here. So here we have just optical quarter. Here we have this pseudo-colored segmentation map. If we have pixel here red and here red, that means their mass spectra are similar. So, and already here you see that this is a great way to get insight about your data, about your samples, and even get something similar to anatomic schematic reconstructed from the red brain atlas. So, but in fact, we're interested in spatial segmentation for the following reason. So let me consider one example, real-life example of working with a segmentation. So here is a data set where we have 3 bacteria colonies. So one bacteria colony here, another bacteria colony here, and third in between. And you see that spatial segmentation, it recovers the structure. And what we can do afterwards, we can select a cluster here, which probably corresponds to this bacteria colony, and we can get a mean spectrum for this. And then we can get also the peaks, which are characteristic for this cluster. The same we can do with another bacteria colony. And then we can analyze what the difference is here. And we can interpret it from the molecular biology viewpoint. So spatial segmentation is important. The motivation for this work was, the problem is that if we just take our spectra and we just cluster them with a clustering algorithm, so what we get is this very inappropriate, noisy segmentation method. So we have developed one approach to solve this noise issue, and we have published it. We have 2 patent applications, nice, but it's not fast enough. So okay, it's fast enough for current databases, for state-of-the-art databases, but soon it will be not fast enough, as for example was pointed out in first keynote session. So we need efficient algorithms. So the motivation for this work was to develop an algorithm for efficient spatial segmentation of noisy IMS data. So now we know what we would like to achieve. The question is how to get there. So, and let me introduce the method, which is based on this key idea. So when we will be doing clustering, we'll be doing clustering not just separate spectra, but we'll be considering each spectrum together with its neighborhood. That means, neighborhood is pixelated. So let me illustrate this idea with a very simple drawings. So this would be just standard pairwise distance between the spectra. So this is one pixel, this is another pixel, and we have spectrum measured, one spectrum measured here, one spectrum is measured here. We can calculate, for example, Euclidean distance or another distance, and we can use it in our clustering. But as I've shown you, it does work. So what we would like to do, we would like to get some spatially aware distance. That means when we'll be calculating the distance between this pixel, or spectrum at this pixel, and spectrum at this pixel, we will be considering the pixels around them in a small neighborhood. This is an example for neighborhood of radius 1. So, for example, we can do this in the following way. So we can calculate the pairwise distance between these 2 blue pixels, these 2 light blue pixels, these 2 green, and so on. And then, for example, we can sum the distances up. This is just one approach, but we'll follow it. And how we can formulate it mathematically. So it leads to a fairly simple distance, which is in fact expressed like this one. And this is nothing but formulation of this idea. So what we do, we go through all these pairs. For each pair, we calculate the pairwise distance, Euclidean distance, squared, and then we multiply it with some weight, and then we sum it up. Very simple. So, and we have 2 parameters. One is radius of the neighborhood. Here is just one, or it can be larger, and we have these weights. But still we have a problem. And the problem is that it's not me who don't like the distance-based clustering. It simply doesn't work in this case because we have a large dataset. We have, even for 200 by 200 pixels, what the distance metrics, definitely half of it, so will occupy 3 gigabytes. And this is fairly small data set. So that means we cannot just use at least straightforward distance-based clustering. So how can we still use this idea of the spatially aware distance? What we do is we do vectorial clustering, which will be equivalent to our distance-based clustering in the following way. So let's map each spectrum into some feature space with some new mapping phi, so that when we take the spectrum and we map it here, we have some point here, some image, and when we take this and map it, we also have some image. And when we will be calculating the distance between these images, we'll be getting our spatially aware distance. So in principle, you see that when we map it, we consider the full neighborhood around the spectrum. So for those of you who know kernel-based methods or SVM, it resembles the kernel trick with a difference that here we deal with distances, and I can show you the phi. And the phi is very simple. So this is the phi. So it looks complicated. So let's start with an example. So for radius 1. So what we do, we take the spectrum measured here, we put it here as a part of our column. We take spectrum from here, we put it there, and then so on and so on. That means we just take our spectrum and we concatenate it. So this is how our phi looks like. And so definitely if our spectrum is from dimension, was of dimension p, then our phi, this mapped, will be of dimension p multiplied with a 2r plus 1 squared. Why? Because we just have 2r plus 1 squared points in our neighborhood. Was it clear with this phi? Yes. Okay, good. So that means we just take them, concatenate them. Okay, we multiply them with these weights. And so this is how phi looks like. We still have a problem. So the problem is that, as I've shown you, we have quite large dimension here of our data because we have p, which was quite large, and then we multiply it with a 2r plus 1 squared. R is large, can be large, so this large. So we use a fast map method for dimensionality reduction. And in fact, this is my favorite method for dimensionality reduction. Why? Because you give this method a distance matrix and some dimension, and it calculates you the points in Euclidean space with these given pairwise distances. So if you know multi-dimensional scaling, this is in fact the same, but it is much faster because MDS is or n squared. Here we just have runtime or n. So what is even better, so it needs really few distances. So it needs to calculate just n to u plus 1 pairwise distance, which is really great for us. I will show why. And so we do not need to store the distance matrix. We can just compute them on the fly. That means we get rid out of storing this huge distance matrix. So this is the algorithm. We first take the spectrum. We map them with a spatially aware mapping phi into this space. Then with fast map, we do dimensionality reduction. And then we apply k-means for clustering of these points. But in fact, this is our conceptual scheme. So what will be the efficient implementation? We can join all these two mappings into one with a fast map, and we can just project our original spectra into low dimensions, and then we can do k-means. Why? Because as you remember, fast map just takes some distances, and you can just explain, okay, let me take not these distances Euclidean this space, but this where you know phi, and then you can just use explicit form of phi to put it into fast map, and you have it in one step. So this is how algorithm looks like. 2 steps. One is mapping, second one just very simple vectorial clustering k-means. So what are the parameters? We have 3 points here. One is weights. Yeah, this weights for the distance, spatially aware distance. So the natural way would be here, just Gaussian distance, just Gaussian weights, and so sigma selected by the 2 sigma rule, and okay, that's fine. So they are quite natural. The further we are from our spectrum, the smaller should be the weight. Second parameter is number of clusters. We do not we can just get rid of it. So we can say, you just specify the number of clusters, I produce the segmentation method. In real life, that's fine. So we have more tricky parameter, this fast map dimension q. And unfortunately, there is no theory about it. So, but fortunately, it does not influence the results too much. So here, the segmentation maps produced with all this algorithm for different q. Do you see the differences here?
Yes.
Yeah, do you see? Where? Between which and which? Probably here and here.
Yeah.
Right, yeah. So, I mean, you do see probably here differences, but, I mean, please guess where the difference is here. I mean, I don't see it. So that means, I mean, there are some small differences, but they're not significant. But, in fact, this is the most tricky parameter. So that means we have this, looks complicated pipeline, but with just one non-trivial parameter, which is great. So, but, I mean, what's special in this algorithm? Why I'm presenting here? Because the complexity of this algorithm is really great. It's linear in time. Moreover, it needs you to calculate just, I mean, n to the, so that means O n distances, which is really fast. Because most of the algorithms, they are all O n squared, like NFTC or something like this. So that means it is really efficient, and this is what we need for our large data sets. Moreover, we can improve it. We can make it adaptive. And the idea behind it that, okay, first we have this, our Gaussian weights. Let's suppose that here we have one region in our sample, this is another one. For example, here is tumor, here is non-tumor tissue. So, and we do not want to consider these pixels when we calculate the distance for this spectrum, because they are just different. So what we would like to have the weights here just less, somehow penalized. And so there is a very nice method in image processing called bilateral filtering, where we can do very simple calculations to penalize them. So that means we can make our weights adaptive, which is nice. Let's check whether it works in principle. We'll consider the segmentation maps and also the runtimes for them. So this is our red brain data set, which I've shown you before, which has 20,000 pixels and long spectrum. Here's just optical photo. Here is schematic from the red brain atlas. Here is a segmentation with a straightforward clustering. You see it is not really green. So these are the segmentation maps with our method for different radius of the neighborhood, with Gaussian weights here are with adaptive weights. So, I mean, first of all, what we see is that this is worse than this. Okay, this is nice. So the second thing, we see that as we increase the neighborhood, the results, they get smoother. I mean, this is what we expected, but still it's nice. So let's now compare the non-adaptive weights with adaptive weights. So, I mean, if you look closer, and if you know the structure of the red brain, you see that here there are some artifacts, like these lines. And moreover, you see these lines here as well. I mean, you see these green, thin lines. And these are definitely artifacts, simply because here we use non-adaptive weights. And when we do this averaging of these neighborhoods, we just took some information from another region. So, and here we see that our idea worked well, and with adaptive weights we don't have these artifacts. But how does it look like if we compare our results, non-adaptive weights, adaptive weights, with the state-of-the-art methods? First of all, we see that if we use one method which does not penalize this noise, the results are noisy. So this is what we would like to prove. Second, this is the segmentation map from our previous paper. I mean, how do you think, which one is better? This one, this one. Wow.
The upper one.
Upper one, I don't know, so actually. I mean, thank you, but actually the evaluation here is quite complicated. I don't know which one is better, this one or this one. But why? I think that this one is better, because let's have a look at the runtimes. This is the runtime for this map. This is the runtime for this map. So you see the difference is 60 times. And this is just runtimes, without any memory consuming and so on. So that means if we compare with our previous method, we get 60 times speed up, which is nice. So what is really astonishing is that if we compare with just plain k-means, we see that we have almost the same runtime, simply because here we map it into low-dimensional space. So that means runtimes are really great for us. So let's check another data set where we have some tumor region. And if we just duplicate image, 2 minutes? 1 minute?
1.
Okay. So we don't see anything here. Here we do see pathology region, which is again nice. Discussion. First of all, evaluation is complicated. I mean, I appreciate that you like my segmentation method, but it's really hard issue here. So why k-means? Because it's fast, simple, and so on. So, and then we have an issue here, and then we have, we can use it for multi-channel image, for example, Raman focal microscopy. And what is even more interesting, we can use it for hyperspectral volume data. That means when we, not for pixel, but for voxel, we have a spectrum. Summary. So first of all, our mapping idea is pixel is considered together with its neighbors. Second point, so it is efficient. It is linear in time and space. And last point, it outperforms straightforward segmentation. So this is the take-home messages, and I would like to finish with acknowledgements. And thank you very much for your patience.